All right. There we go. Let us get started. Are we recording? Recording on this computer. Good, good, good. Y'all can hear me?
Yep.
Okay, thank you. So what we're going to do today is we're going to finish up our discussion of GFS transition into Hadoop. Oops. And so the only thing left we have to talk about with GFS is mutations or attempts to write to the data file. And so I talked about how master metadata is stored to do mutations. I'm just going to give you an example of how mutations actually work step by step so you can see what they're doing. And then I think we're probably about out. I will talk a bit about fault tolerance in GFS as well. So these would be appends or writes to the file. And again, GFS assumes that appends are the norm. So every replica of a chunk needs to maintain consistency. And this is always the case with these distributed file systems. When you go to do a write, you have to make sure that the write completes in the same order on every replica, or that it doesn't complete, that it fails on every replica. Otherwise, you get inconsistency. So we have this idea of chunk leases. I think we talked about this yesterday. So a chunk lease is granted by the master to one primary replica. And so every time you go to do a mutation, you're actually going to talk to the primary replica. So when you do an fwrite through the GFS file system, you'll actually get back information about who you need to negotiate that write with. And so here's an example of a client writing data to a file. So first, the client identifies the chunk to write to. Okay. So where in the file do we want to write? Second, the client asks the master for chunk replicas and the identity of the primary. So who should I be updating, and who's responsible for managing the consistency of those updates? And then next, the client pushes all the data to the replicas. So it's the client's job to make sure that all the replicas get the data to be written. And of course, it's probably providing it in some order, but the order that matters is the order that it gets provided to the primary. Okay. So next, the client sends a write request to the primary, who chooses the order of mutation. And applies the mutations to the replicas. And the primary sends the order of mutation to the replicas. So it tells the replicas, hey, you just got some data to write, and this is the order that you need to write it in. So this is the order that you need to take those write operations and apply them in to maintain consistency amongst all of us. And so once the replicas have written the data, the primary replies to the client, that the op is complete. So this is in the case where everything works, all right? So the client pushes the data down to the all the chunks, and then tells the primary chunk, I want to write this data. And then the primary chunk decides what order it's going to be written in, tells all the replicas, write this data that you just received in this order. All the replicas signal back to the primary, okay, I did that. And then the primary will, at that point, signal back to the client to say, all right, we're done. Everybody wrote the data in the same order, and so everything is consistent, so you can now assume that the operation completed successfully and proceed. Okay? So any questions about this before I talk about, well, what happens if errors crop up? Which they will. So if errors are encountered, the client request is considered to fail. And the modified region of the file is in an inconsistent state. On some or all replicas. So if an error happens, we don't really know what happened. We just know things went wrong. So that means is that what that means is that maybe some of the replicas didn't write the data in the right order, maybe they didn't write all of it, maybe all of them got screwed up. We have no idea what the actual state of the file is on the primary or any of the replicas at this point. We just know that it's not good. All right. So clients are expected to retry pushing data and requesting or re-requesting, if you prefer, a write at the primary. All right. So the classic computer science solution to a problem. Let's just try it again. Maybe it'll work this time. Yeah. Okay, sure, why not? You sort of wonder, if it didn't work the first time, why would it work the second time? But it often does, which is very bad, actually. That shouldn't happen, but it does. So if if the write continues to fail, the client will contact the master to restart the entire write request. So the assumption here is that if we keep retrying this, right, and it's not working, then there's something wrong with one of the replicas. It's dead, it's not a replica anymore, something, it can't communicate, its disk is full, something weird is going on with the replica. And so what we're going to do is we're going to recontact the master, because the master at this point should now have updated its information about the replicas through its heartbeat. And so we're going to say, hey, who are the replicas and who's the primary? Tell me again, because I need to retry this, and it's not working with whatever information you gave me when I asked the first time. And the assumption is you're going to get something different, and you're just going to retry the right request. And so the master maintains what's called a chunk version number. It increments whenever a new chunk lease is granted. Okay. So every time a chunk lease is granted, the version number bumps up by 1. So the master and chunk replicas record the new version number before any clients are given access to the chunk's primary. So the chunks know, well, which version number are we on? Somebody's asking for access to the primary, okay? And if a replica's chunk server is unavailable, which would be the assumption if this write is continuing to fail, it will miss the new version number, right? If it's failed, it's not going to be able to, or it won't try to ask for the new version number when this write request that was failing was attempted, okay? So when a chunk server becomes available, its stale chunk will be detected by the master during a heartbeat communication. Because during a heartbeat, it checks which chunks it's responsible for on the chunk server, but it's also going to be checking those version numbers to see if they match up with the version numbers that the master knows are correct. And if they don't, then it knows, well, I don't know what happened, but you're out of sync, okay? And if that happens, then the stale chunk is garbage collected. And a new replica is created, okay? So what happens is the master says, all right, I don't know what happened to you, but your chunk is out of whack somehow, and so we don't know how it's out of whack, so the whole thing is going away. So the stale chunk is simply marked for garbage collection as being available for deletion, and then a new replica is created from one of the replicas that's actually in sync. And so the assumption is that up here, if the client's trying and failing, down here, this is going to happen. So up here, when the client finally says this isn't working, and it asks the master, hey, give me that primary and those chunk server replicas again, it's going to get the new replica that's been created and not the old one that somehow disappeared or went dark. Okay? And so then the assumption is at some point, you know, this is going to happen. Maybe you ask and it hasn't happened yet. You're just still going to get that chunk server if it doesn't work. So this is going to fail again. It's going to fail again. If you keep doing this, at some point, you're going to get the updated information that the master has corrected things. It's going to work, and then you can proceed onwards. Okay. Any questions about that? So the approach isn't sophisticated, but it's very effective. I don't know that it's super efficient, but it's effective. It's going to work at some point.
How exactly do the heartbeat messages work? It sounds like they'd have to transmit a lot of data if you're having to update the status of each chunk every time and the version number and all that.
Yeah, they try to minimize it. So basically the heartbeat, I don't know exactly what it contains, but for the chunk server chunks, it's going to contain the chunk IDs, that 4-byte or 64-bit, I guess. So 8-byte unique identifier, and then the version number for each chunk that it's passing back. So that's not very much data. And then the master is going to be checking that. And the other thing is that, as I said, I'm pretty sure the master doesn't contact all the chunk servers all at once. It's polling them in sort of a round robin fashion. So it'll ask one, it'll check it, it'll ask the next one, it'll check it, and it'll go through all of them and then start over again. And so it's doing that to minimize communication as well, because it's trying to keep a hold of how much work it does so that it doesn't become overwhelmed, and then that'll slow down the clients. So, and it's 64 meg per chunk. I don't know how many chunks you're going to get on a typical sized chunk server, but it's not going to be astronomically high. It's not going to be that billions that they were trying to avoid. It's going to be thousands probably of chunks per chunk server. Other questions about this? All right, so let's talk a bit about fault tolerance and then we can move on. So remember that it's assumed among, it would be hundreds or maybe even now thousands of servers in that GFS cluster. Some are always down. I think that 15% is the number that they assume. So to maintain high overall availability, GFS provides fast recovery and replication. Fast and efficient. So basically what this means is that once you slam a new hard drive in there to get rid of the old one that's dead, it's very quickly going to be brought up to speed. And that's important because the system can't be like RAID 5 where it wastes hours trying to get a new replica online. That's not going to work. So both the master and these chunk servers are designed to restore state and restart quickly. So it turns out that GFS does not distinguish between normal, termination, and fail. So if you bring down the chunk server gracefully, or if it simply dies, GFS doesn't care. From its point of view, it's simply no longer available. Okay. Clients may need to wait briefly. for a timeout on an outstanding request. Okay, and if that happens, they just reconnect to the presumably restarted server and then retry the request. Okay. And so chunks are replicated across multiple chunk servers. And the master is responsible for ensuring sufficient number of replicas. And for creating new replicas. When a chunk server fails. So a sufficient number would be to maintain fault tolerance, but also to maintain efficient performance, depending on how many people are actually, how many clients at any given time are hitting the array. Okay. So each chunk server uses checksumming. So checksums to detect data corruption in a chunk. On a read or a write. Okay. When errors are detected, the client is informed and asked to use a different replica. That would be on a read. Okay. And the corrupted replica is marked for garbage collection. So no attempt to correct it. We just say something's wrong here, get rid of it. Okay. And so the master during the heartbeat will recognize, okay, that replica has been garbage collected, so I need to create a new one. It will create a new one somewhere, and on it will go. Okay. Now, what about the master? This is always a problem with these distributed file systems, is that if the master goes down, all hell breaks loose. And so the master is also replicated for reliability. Okay. And it duplicates its operations log. On multiple machines. Okay. And you remember that operations log is just the list of operations that is performed in order. And so if the master fails, external monitoring, how would that work? Restarts. Restarts it almost immediately. So there's some set of external monitors that are keeping an eye on the master, and if they ever notice the master goes down, they immediately move to restart it, okay? So if its machine or disk fails, a new master is started. On a separate machine. And the DNS tables are updated to map the master's name to the new machine. Okay, so the way they do this is the master simply is operation log is used to replicate it on a new machine, and then the DNS tables are updated. So when you're asking for master, you always do it by qualified domain name. And so since the DNS tables have been updated, you're just going to start getting a different IP address for the quote-unquote master. And so from the client's point of view, it doesn't really recognize that anything's changed, but it starts getting answers back again. Okay. And so GFS also maintains what's called shadow masters to provide read-only access to data when the primary master is down. Okay. So this provides readability, at least, to the data while the new master is being brought up. And so they don't talk about this specifically in the paper, but I think the way this works is that the shadow masters, whenever they get a write request, they ignore it. And so what will happen at the client's end is they'll see a timeout and they'll reissue the request, and hopefully the new master is up by the time they do that. And so then they'll actually get the information they need about the chunk replications, the primary, and all that other kind of stuff, right? So if you do a DNS table switch immediately to a shadow master when the master fails, and then another DNS switch to the new master when it's up, you'll definitely see no interruption in service in terms of read requests, okay? You'll only see an interruption in service based on write requests, and GFS is built under the assumption that write requests are rare, and so the expectation is that this is not going to be a major problem for the majority of clients accessing the cluster. And that's, I mean, that's not all the details about how GFS works, but that's all the details they were willing to give out in the paper. And so that is Google File System. So it's a highly distributed, highly available, highly scalable, highly efficient distributed file system if your pattern of file usage matches the pattern that they're designed, that GFS was designed to support, okay? If it's Jesus God, if it's a random, someone's fucking with me. I don't know. Anyway, I can't say that, sorry. I wonder if someone's messing with me. Anyway, if you don't support this kind of file access pattern, then GFS will still work, but it's probably not going to work well. So, But for large data stores, this is not a common pattern. Okay. And you can see why Google's doing this, right? Like, what do they really store by and large? Some sort of map of the web and the information that's stored in there. And so that information isn't really changing much very often, but it's certainly growing. And so from their perspective, this is a perfectly reasonable model to use. Yeah. Any questions about that? All right, so let's talk a little bit about Hadoop. And I'll just tell you right now that Hadoop is an all-encompassing moniker for a whole bunch of different things. So if someone asks you, and I get this all the time when we have our students do interviews, they'll say, can you program in Hadoop? That question makes no sense, all right? That's like asking, can you program in Microsoft Server? No, because it's not a programming environment, but there are parts of Hadoop that support programming like Pig and Hive and Spark. And so yes, we can program in those, but Hadoop is an overarching architecture, a file system, a large data cluster system, and then a whole variety of add-ons that allow you access to the data to do certain types of workflow, right? So Pig is completely different than Hive in terms of what it's good at, which is different than Spark in terms of what it's good at, and so on. All right. So one of the things we didn't talk about with GFS is the corresponding MapReduce operation, which is designed to support highly parallelizable operations in a very efficient manner. And so, of course, this is duplicated in Hadoop along with HFS, which is the open source version of GFS. And so we're going to talk about MapReduce here. Sweet Hadoop. Hadoop. So this is an architecture to support storage, transformation, and analysis of very large data sets. Okay, and Hadoop is part of the Apache Software Foundation. ASF. And it's founded in 1999. ASF is to support developers' release and support of open source software, to support developer release and maintenance. Well, so we'll say and support open source software. Projects. So lots of people release under the ASF open source guidelines, and there's a bunch of these different open source consortiums, and they all have slightly different EULAs, end user license agreements. But Hadoop's part of Apache Software Foundation. Okay, big one of the big ones. So many companies have participated in Hadoop's code base. All right, so many companies have participated in Hadoop's code base. So this is usually part of the requirements of any of these open source projects is that you can use the software without charge. Sometimes you can use it only open source without charge. Sometimes you can actually use it commercial without charge as well. But any changes that you make to it have to be pushed back into the original code base. Okay. So this includes Microsoft, Facebook, Google themselves are offered stuff here, and most importantly, Yahoo. And so Yahoo no longer uses an exclamation mark in their company name, so I think I won't put it here. And Yahoo has contributed significant work to the core system. Okay. So I think Yahoo's done by far the most work and the work on the most important parts, which is interesting. You know Yahoo still exists, right? I mean, you know this. Are you old enough to know what Yahoo was when it first came out? I don't even know. I mean, I'm just old, so
Vaguely.
Vaguely. So Yahoo was originally a internet search engine, but it was very different than Google. So instead of actually typing in a query and then getting back results, what it did was it tried to build we would call it an ontology or taxonomy, but it basically tried to build a way of categorizing information on the web that started at a very high level, and then you would go down to a slightly lower level and down to a slightly lower level and so on, like a tree. And so you would navigate through this tree to find the place where you thought the information was that you wanted to retrieve. And that was their original model. And of course, that didn't last forever. Google definitely blew that up, although there were many companies prior to Google that were actually doing natural language processing-based keyword query search. And so Yahoo now is owned by Verizon, I believe. I actually have still a student working there. And so I'm not really sure what their deal is, like what it is that they're actually offering. Obviously, whatever it is isn't making a lot of money, which is why they had to sell themselves. And you remember that, what was her name?
Marissa Mayer.
Yeah, moved from Google over there, and that was going to be the big savior, and then that didn't work out. But I think she escaped with a lot of money, so that was good for her. They were a great company. I think they're still a great company. They just didn't work out for them. So startups die, and then major companies like Netscape and Yahoo and AOL also die. It just takes longer because they have more money, I guess. So, do you guys still?
Didn't AOL, like, my understanding was AOL actually did a good job of pivoting under all the chaos of change, and are actually one of the biggest, like, outside of YouTube, or one of the biggest, like, servers of, like, media, or at least that was I remember one of their executives giving a talk about that several years ago.
And that's what he claimed, was it?
Yeah.
Yeah, well, we'll go with that then, sure. No reason he would lie about that.
Sure.
So there was the AOL Time Warner Media merger, and that was sort of peak AOL, I think, and then that fell apart. But AOL lives on. It used to be you would get AOL CDs everywhere. Like, seriously, you buy a box of cereal, a freaking AOL CD would come in it. I'm not kidding. And so that doesn't happen anymore. But AOL lives on, and I think it's actually fairly popular with a certain segment of the population that just doesn't have easy access to high-speed internet. And so rural, other areas like that, they're still using dial-up, okay? We live in Cary, we live in Raleigh. We have like AT&T fiber and Google fiber now right outside my house. Both of them are trying to offer it to me for $70 a month. And I'm like, I thought I was gonna get a good deal, but anyway. But if you live out in the boondocks, like, there's no way they're gonna build out to you, because it's completely not cost effective to do that. It's also illegal because they said they would and now they're not. But anyway, I mean, I guess that doesn't matter if you're a big company. And so your choices are things like satellite, which is unreliable, or everybody still has hardline, and so you can use dial-up. 56K is probably the fastest you're going to get, but if you don't care, then that's fine. And you'll probably be using AOL for dial-up because these other companies aren't offering it. So yeah. So I read an interesting article about, I don't know if any of you program in HTML, CSS, but the new big thing in CSS is CSS Grid. And CSS Grid is a big thing because layout of a web page is an incredible pain in the ass, and I can definitely confirm that. And then if you have to support multiple architectures like phone, tablet, large format screen, obviously the layout's going to be different for those different architectures. And so it used to be that you had to hard code this shit in for each one of these. But what CSS Grid does is it allows you to define this grid, and then you can specify one or more contiguous blocks as having some identifier. And then what you can do is the actual layout is separate. So you define the grid, and then you can redefine the grid to have those identifiers occupying different blocks inside the grid for a different media source, a different architecture. So then the system just automatically reconfigures for that because you've told your HTML, CSS, okay, the header goes in the header blocks. And then if inside the grid, CSS grid, you change what the header blocks are, it just immediately updates the layout for you. So it looks really cool. I'm actually going to try it out and see how it works. It's now finally supported by all the major internet browser vendors. Now that is it Edge, whatever the new Microsoft internet browser is, and it even supports Internet Explorer back to probably about IE8. But interestingly, the reason I say this is that the recommendation of the guys who worked on this and who use it is that your default grid layout should be for cell phone, okay? And then you should update that grid layout if you see that you have a better screen real estate or some other property that you think is useful. And I realized, oh yeah, that would make perfect sense, because if you're sitting on a 56K modem, you probably want the phone layout, right? Because you don't have the bandwidth to download massive amounts of information. And even though phones are pretty fast now, people still do try to be efficient on their phone layouts. And so you could detect, for example, well, how are you connecting to the web page? And then you could just give them the default, which would be the phone layout, if they were connecting by anything below a certain bandwidth. So that would be cool. Yeah. HTML, CSS is a real sort of dog's breakfast. And so anything to make it better, I'm all for it. Yeah. I mean, doing certain things, especially when they switched over to CSS as being the default, a lot of things didn't come along very easily. So things like table properties and other things like that, it's a bit of a mess. And so I spend way too much time hacking HTML, CSS, and then testing all 4 browsers to see whether it looks the same in all 4 of them, which is incredibly frustrating. Yeah. So if you're thinking about becoming a web designer after you're finished, and you haven't tried it yet, you should probably try it and see if you like it before you do it. All right, so what does one of these Hadoop clusters look like? Let me draw it for you. Oh, and I should just mention that, like, you notice all the main commercial companies are helping out here with this open source implementation. So this is not uncommon. So they're not completely bad. I mean, Don't Be Evil's gone out the window a long time ago, but they are still working hard to try to provide open source solutions that are going to be useful for them, but then useful for other companies as well. So they're giving away some competitive advantage. I think I mentioned that Facebook built a new kind of server rack that really reduced the overhead of wiring up things, and they just released that and said anyone who wants to use a server rack design, knock yourself out. And lots of people are. So, anywho, so you have a client, of course, as always, sitting up here at the top, and then you have file read writes. So we'll call this file IO. And I'll put a little line underneath here to differentiate that on one side we have the client and on the other side we have the cluster. And so there's going to be something called a name node if you're doing file IO. And this is using HDFS, Hadoop file system, which is basically GFS, open source implementation. And so this is going to write down to a data node task tracker. So this is something that manages all the requests that are coming from all the different clients and prioritizes them, orders them, and executes them so that they're contiguous. And then underneath here, you're going to have some file A, block 2, file B, block 2. And obviously, I'm only writing 2. These are the equivalent of chunk servers to actual data servers, but there's hundreds of thousands of these storing hundreds of thousands of what they call blocks, which are the equivalent of chunks. Okay. Now, the other thing you can do is you can actually ask out for a MapReduce job. Okay. So you want to compute some parallelized job. And so there's a job tracker. Just like there's a task tracker, and then this is MapReduce. Okay, and so this guy talks down to a data node tracker, task tracker. Okay, same thing, because a MapReduce job is just a bunch of operations on files, so it goes down to the same data node task tracker that an IO operation would. It just goes down with a different set of requests. Okay, and then underneath here you have, and you have a whole bunch of these. They all have their own okay, and so you have this name node and this job tracker, and this is sort of the master, if you want to think about it like that. So it's responsible for both of these, okay? And then you have the Hadoop distributed file system, which basically does what GFS does. And then you have the Hadoop job MapReduce, which basically does MapReduce operations on the same data. So same architecture underneath here because you're talking to the same data, but it's the open source implementation of Google's MapReduce. Okay. So two critical components of Hadoop are HDFS, which is a Hadoop distributed file system, and the MapReduce algorithm. Okay, so these allow efficient parallel computation. On very large data sets. Okay, so you can recognize that if you're thinking about parallel computation, you need both of these, right? Because this is the part that actually we're going to talk about that splits a job up into independent pieces that can be parallelized across different data nodes, and then combine back together to a final result to send back to the client. But you need this architecture as well, this HDFS architecture, because if you don't have this, then you don't have duplicates of the files. And if you don't have duplicates of the files, there's no way to do efficient parallel computation. All right, even if, will it come back on or do I have to move? I bet I have to move. Move a little bit. Walking, walking, walking. Huh, didn't come back on this time. I don't give a shit. You can still see me, right? Yeah, I can see the confidence monitor data. You can still see me. And you can still see the screen. And I don't like to, I don't use lights in my office, so maybe I'll just leave these off all the time. Anyway, you need both pieces of this in order to get MapReduce to work effectively. Okay. And so that's how that's set up. So are there any questions about any of that? I mean, I know that we haven't talked specifically about the details of the job tracker and how data nodes and task tracking differ from what I showed you for GFS. In reality, we're not going to talk much about HDFS at all because it really is just GFS. And you'll see exactly how it ties into this. There's no mystery there. We're going to focus on what's MapReduce and how does it get prioritized and what kinds of things can you MapReduce. So MapReduce supports efficient parallelization of jobs, but MapReduce, as with anything, is not something where you can just give it a task and say, parallelize this for me and make it fast. Okay, you have to properly structure the task so that it could be parallelized, and you actually are responsible for a lot of that parallelization decision-making prior to calling the MapReduce job. Okay, and as you know, probably parallelizing jobs is sometimes really easy and sometimes impossibly hard, or impossible for that matter. And so personally, and I'm not the only one who thinks this, in the undergraduate curriculum, one of the things that we probably don't spend enough time on is talking about parallelization, because all of the CPU efficiency improvements, all of the sort of large data set improvements and other things are really relying on parallelization, which is an incredibly complicated thing to do. And so we should be helping to try to explain not just what the fundamentals of parallelization are, like deadlock and other things like that, but also how do you go about converting certain patterns of computation into something that's independent in the way that you can actually do parallelization, right? So GPGPU, general purpose graphics processing unit, is used for parallelization all the time because the GPU units are themselves parallel computation units. But again, if you can't convert your task into something that can actually efficiently use all of those GPUs all at the same time, you're not going to get any advantage. So, any questions about any of that? All right, I will let you go, and I will see you on Friday. Thank you.
Thank you.
Thank you.